Hey guys, welcome to Climate Day 2. Today we're going to talk about porosity, permeability, capillarity, a couple new words, and basically they're all talking about the way water travels through the soil. All right, just a reminder, you got your Castle Learning post-test that will be due Friday at midnight, so please make sure that you do a good job and get it in on time. It will close the window. All right, so zone of aeration versus zone of saturation. If you guys remember, aeration is basically the dry sponge, the dry soil, and saturation is the wet sponge, where all those pores, all those openings are already filled with water. Okay, so aeration will allow water to flow through it pretty well because there's nothing in it. Zone of saturation is already filled, so you're going to have less water flowing through. Okay, so I want to first start by showing you a little clip. Check it out.
Lower Manhattan remains eerily dark and partially underwater after 18 people lost their lives due to the storm here. My colleague ABC's Juju Chang spent last night wading through a flooded downtown and today went to survey the damage.
What's going on?
It's closed. You have to go to the route.
It took us much of the day navigating through streets made treacherous by Sandy's fury.
Got hit by a wave.
But we managed to rendezvous with the Coast Guard at a shuttered airport in New Jersey for a harrowing bird's-eye view of this wounded city.
Yeah, look at this whole neighborhood right here. Oh, man. Yeah, look at this whole neighborhood right here. That building's gone entirely.
Their mission to get a more accurate picture of Sandy's impact
More flooding down here on the left side.
and search for stranded souls.
I had to rescue a couple male, female, diabetic, and she was diabetic.
Last night, New York's rivers surged above the banks of Lower Manhattan with a record 13-foot wall of water. Today, you could see the damage everywhere. The city's vital infrastructure, its underground subways, crippled. The system that carries 5 million riders every day, still a deluged tunnel of darkness.
Okay, so the whole point of showing you that was to show you that the water really had nowhere to go. Hurricane Sandy was a big storm. I mean, it wasn't a Category 5 hurricane or anything, but it did have big water surges. It hit at high tide, right? The storm surge was really high, so we got a lot of water on the mainland. But the thing is that Manhattan is very urban, very highly developed. It's all cement. And when it's cement, you will not have infiltration, right? It's basically an impermeable rock. So the water has nowhere to go, so it just pools. And that's why the flooding was so severe. It had nowhere else to go. You talk about the same amount of water hitting out east, out by like Riverhead or Montauk, where it's all like farmland and soil, that water can seep into the ground. But if you're talking about Manhattan, the water has nowhere to go, so it just sat on top like that. All right, so let's talk about the word porosity. You guys have probably heard of the word before. We're talking about pores, okay, which is basically open, empty spaces, okay? This is empty spaces in the soil. Okay, so it's going to be between little rocks, between cracks. It's basically empty spaces in the soil that water can potentially go through or sit in. All right, now there are some things that will affect porosity. There are some soils that have good porosity, a lot of openings, and soils that don't have good porosity, very little openings. All right, so a couple things that might affect that would be shape of the particles, how tightly packed it is, and if it's sorted or not. But one major point that I want you to know is this. Grain size has no effect on porosity. Okay, so let's take a look at a couple pictures, and all of these are in your notes, by the way. So high porosity, this means that it has a lot of spaces. Okay, low porosity, not a lot of spaces. And you can kind of see it in the pictures, right? But take a look. If they are all the same shape, then they kind of sit on each other, but then they leave all of these open spots here. So that's going to give you good porosity, right? Look at it on the other side, on the low porosity side. If you have all different sized particles, if they're angular, if you shake that, they all kind of settle in kind of like a jigsaw pattern, and they fill up those spaces. So you have a lot fewer openings, okay? So same shape leads to more porosity. Different sized shapes, different shaped particles, if they're angular, they kind of fill up those spaces. Next, interconnected. This is loosely packed. This is tightly packed, right? If they're loose, they have all those openings, right? That's a lot of potential spaces that can be filled with water versus tightly packed, right? This is why, come springtime, you're going to want to mix up your garden beds to allow for more water to permeate the soil and also allow more gases to get into the soil, right? Carbon dioxide. And then the last one, let's talk size. If they are all the same size, up top we were talking about shape, now we're talking about size, does that same thing. They kind of settle on each other and leave those good pores. If they're all different sizes, right, this is unsorted, they're going to kind of jiggle and settle in between, leaving very few pores, okay? So major things to consider. You have shape, you have packing, and you have size, okay? But size in terms of sorting, okay? If they are all the same size, right? Look at this diagram down here. This is the big point that I made on the previous page. These are all the same size. They're all small, right? This is all small. These are all medium, and these are all large. But they are sorted, right? This, yes, is sorted down here, okay? Take a look. They are still going to hold the same amount of water. So even though they're different sized, the fact that they are all the uniform, the same sorted particle in each beaker, they will have the same porosity. Okay, that's what we meant before when we said grain size has no effect if it is all uniform, if it's all the same, if it is sorted. Okay, so what I mean by this is picture this beaker as being $100. Okay, this would be 100 ones. This would be 25s. And this would be 10 tens, right? They all have the same porosity. They all add up to 100. They're just in different denominations, okay? So in beaker A, you have a whole crap load of really tiny pores, but they're still going to be able to fit the same amount of water if you were to pour water in versus beaker C, all right? Fewer pores, but those pores are a lot larger. You're still going to get the same amount of water, okay? Next, permeability. So this is the ability for the fluid to flow through the material. Remember, we said if it is permeable, it can. If it's impermeable, like bedrock, it cannot flow through. And then last year, when you did cell membrane, that's selectively permeable or semi-permeable. Permeability rate is talking about how fast the water goes through, okay? And again, we're going to talk about it once again, like we did it before, factors that affect it. Particle size, packing, sorting, and temperature. These are the factors that will affect how long it takes for the water to flow through, or if water can flow through it at all, okay? So let's take a look at the diagrams. Again, you have these on your note sheet. So high permeability, these can flow well, or versus low permeability, they either cannot flow or they flow poorly. Okay, so the first thing, pebbles and sand grains, water flows through quickly versus silt and clay. So the first thing is talking about size. The larger grains, look at how big these pores are. Nice big pores. Water's going to flow through pretty easily versus the smaller grains. Smaller grains, there's going to be more friction. So it's going to be a little bit more difficult for the water to flow through. It's going to take longer. Okay? It can flow through, it'll just take longer. All right, next one. Water can pass through quickly versus the one that's on the right. This one is talking about packing. This is loose, this is tight. Okay, loosely packed, you got all those open channels. If it's tightly packed, the water can probably still go through. It's just gonna have a lot more difficult time to get through. Or it won't be able to get through at all if it's that tightly packed. Okay? And then C is talking about sorting. This is uniform, if they're all the same size, and this is unsorted. Take a look. If it's uniform, you got those nice channels that are easy to access. Water can flow through nicely. If it's unsorted, just like mentioned before with the porosity, all those open spaces got filled up by the smaller particles, and it's going to be really hard for the water to flow through. All right, so size, packing, sorting all play a role here. And then if you remember just before, temperature. We said it yesterday. If this was frozen, water wouldn't be able to flow through, right? This would all just be one chunk of ice and water cannot flow through. All right, capillarity, you guys might remember capillary action. This is upward movement of water, water moving up against the force of gravity. And this is how roots pull up water. Okay, now couple things for you to really remember. This, smaller particle size, faster capillarity. So the smaller particles there are, the more capillary action you will have, and the more water retention you will have. All right, I'm going to define that. Retention means ability to hold on to water. All right, that means you pour water into the beaker, water flows through it, but then the sediment that's in the beaker is going to hold on to more water. Not all the water is going to flow through. Okay, so if we were to graph these, the smaller the particles, the more capillarity. So this is going to be an indirect relationship for both. The smaller the particles, the more water retention. They're going to hold on to more. And that's because they're going to have more friction. All right, or more surface tension, right? So smaller particle, faster capillarity, and more water retention. Okay, capillarity. Smaller grains allow for more capillary action faster. So the smaller grains, water will travel up higher and faster. All right, so here's what a couple regions questions are going to look like. Diagram below shows the relative sizes of particles from soil samples A, B, and C. Equal volumes of each soil sample were placed in separate containers. Each container has a screen at the bottom, so there's a screen at the bottom so water can flow through at the bottom. Water was poured through each sample to determine its infiltration rate. how fast is water going to flow through it, essentially. So they're all uniform. The only difference is size, right? This is a whole bunch of small sized. These are medium and these are large, but they are all uniform. Okay? Which graph best shows how infiltration rates of the three samples would compare? Which one is going to have water flow through it the fastest? Which one has the biggest pores? So that's going to be choice 1. Okay, water's just going to have an easier time to flow through. And this is because it had the screen at the bottom. If this was a closed beaker and they asked how much porosity they would all have the same porosity, right? They all hold the same amount of open space within them. But this question was saying which one's going to allow water to flow through it faster? And that's the largest sediment, C. Soil with the greatest porosity. So which one is going to have the greatest empty spaces in it? That's going to be well sorted and loosely packed. 2, the diagrams represent 2 identical containers filled with non-porous uniform particles. The containers represent models of 2 different sizes of soil particles. Compared to the model containing larger particles, the model containing smaller particles has... All right, this is one of those questions where you got to be careful on the wording. The model containing smaller particles, whatever choice you choose, has to be talking about this one, okay? So if it is smaller, it will have less permeability and it will have greater capillarity. Remember what we said, the smaller the particles, the more capillary action they have. All right, so with the remainder of this lesson, so we got through these 2 pages. I want you to go through these pages, just a whole bunch of graphs to make sure that you understand all the relationships that we discussed today. There will be the answer key posted in the answer key folder, so feel free to check that out when you're done. All right? Hope all is well. Stay